In a science laboratory, a 1 kilogram mass is suspended by 2 taut strings. The tension forces in string 1 and string 2 are T1 and T2 respectively. Calculate the magnitudes of T1 and T2. All right, here we have a 1 kilogram mass, 2 taut strings. Taut means tight, straight. The tension forces, and we're looking for magnitudes. Okay, and they've given us a little diagram. Now we need to turn that into a force diagram where our body is just a point. And again, we're going to use vector methods. So we're going to have a reference to our I and J. And here is our mass. And our mass has a weight force acting down. And that's going to always be mg. Okay. And it's not resting on a surface. So that means that there is no normal force acting on that object. However, I have a string with a tension T1 acting in that direction. And I have another string. This thing is jumping to different things here. Another string acting in this direction here, which is T2, and they've given me an angle of 42 degrees there. All right, first thing we're going to do is we're going to define all of our variables. So we're going to let R be our resultant force, and we're always going to define our resultant force in newtons. Okay, T1 be the first string tension force in newtons, and T2 be the second string tension force in newtons, and let W be the weight force in newtons. Now this thing is held in place by taut strings. It is in equilibrium. Okay, so we're going to say object is in equilibrium, therefore my resultant force is equal to 0. Okay, and we can say that R is 0I plus 0J. Our W, well, let's have a look. Our W is acting in the negative J direction, and it's mg, so it's negative mgj. But now they've given us the mass, and we know that G is 9.8, so we can actually write that as negative 1 times 9.8 J, and that's just going to be negative 9.8 J. Okay, and our T1, well, T1 only acts in the I direction, and it's positive, so it's just going to be T1I. Notice I don't put a vector squiggle underneath the T1 because that's going to be the magnitude of that force. And T2, well, let's have a look at where T2 is acting. Well, it's going in the negative I direction and the positive J direction, and it is going to have components. So I've got a cos ratio for my I component and a sine ratio for my J component. So I'm going to have negative T2 cos of 42 degrees I plus T2 sine of 42 degrees J. Okay, so I've now set up all my different forces, and I'm going to say that my resultant force is going to be my sum of all my forces, so T1 plus T2 plus my weight. And we've already said that R is 0, so I'm going to have 0I plus 0J is equal to T1I minus T2 cos 42I plus T2 sine 42J minus 9.8J. Okay, and now I can collect my I and J components. So I've got 0I plus 0J is T1 minus T2 cos 42I plus T2 sine 42 minus 9.8J. And hopefully you can see that we're going to have a simultaneous equation here. So if we equate our, let's start with equating our J components, because then we can get rid of one of our unknowns much faster. So T2 sine of 42 minus 9.8 is equal to 0. And so T2 will be 9.8 over sine of 42 degrees. And that gives me 14.6 newtons for T2. If I then equate my I components, and substitute T2 equals 14.6 newtons, what I'm going to end up with is that 0 is T1 minus T2 cos of 42 degrees. And so T1 will be T2 cos of 42 degrees, and it'll be 14.6 cos of 42, and we end up with 10.9 newtons. So therefore T1 is 10.9 newtons and T2 is 14.6 newtons.